Now, we've already studied the advanced topic on motion and rates, and we've studied the extension 1 topic on vectors. Now, this short topic on projectile motion is an extension topic, and it brings both of those concepts together. Now, a couple of important differences. In our advanced motion topic, the movement was all in one dimension. So remember, we imagined maybe a ball bouncing or a stone dropping down from a cliff, or perhaps an object moving along a number line. And although we were able to plot the movement in some way, when we plotted it, we actually said that x was its position or its displacement, and we plotted that on the vertical axis, remember, and we had time on the horizontal axis. And we were really careful to note that any plot that we came up with was really just showing where our object was in space on that number line, or perhaps vertically at any one time. It was not a picture of the path of the ball or the object. In this case, we have got movement in 2 dimensions, and so we can plot it on an x and a y axis, where we are actually plotting the path of an object moving through the air as we would see it from side on. Now, we're separating the movement into horizontal components, or how much it's moving forward, and vertical components, as in how much it's moving up or down. And so they're represented by x and y, which are both functions of time, which is t. That makes sense. And points on the path might be specified at times as position vectors relative to the unit vectors I and j. So if you imagine the unit vector I on the horizontal and j on the vertical, then if you were told to say that an object at a certain time passes through a point that is specified by, let's give an example, let's say 5i plus 7j, then you'd know that if you go along here 5 and then up 7, perhaps there's a point here, 5, 7, where the position vector from the start to that point can be specified that way, or perhaps even in column notation, and that gives you some information about where it is in space at that particular time. Now, to know much about an object that's flying through the air, you really need to know what's happened at the beginning. What's the angle that it's taken off at, and how fast was it going in the beginning? So initial velocity is key, and it will always be mentioned in your question. Now, velocity is a vector, so it must include magnitude, which is just the speed that it's traveling, or the size of the vector, but it also has to include direction, and that includes the angle of inclination, which we generally take as being the angle from the horizontal. Velocity can be separated, though, into its horizontal parts and its vertical parts. So we have this new notation here of x dot and y dot. Now, when we saw x dot in our advanced motion unit, we considered that it was the first derivative of displacement, and so we were calling it velocity. So this is somewhat familiar, but we've got to remember that here it's just velocity in a horizontal direction, and the y dot is the velocity in the vertical direction. And it might be negative if, in fact, the object is dropping. You won't tend to see this one being negative because we're generally working, or we can set our axis up as we like, and it makes sense that we're following the path of something that's moving and is not actually going to come backwards at all. So we generally take forward movement as being in the positive direction, and this will always be positive. Now, initial velocity might be given to you in 2 different ways. Now, this is not a big problem. We can actually use basic trig, and we can use Pythagoras' theorem to go between these 2, and this is really quite straightforward. Now, it could be given as a vector, and so it might be given in column notation or in component form, and what that's doing is it's breaking the velocity up into the horizontal part and the vertical part, where each of these are your horizontal and vertical components. They might even just say x dot equals and y dot equals and let you go from there. Or they might say what the total velocity or the total speed is, and that's taking both directions into account in one go. And in that case, they'll tell you what the angle of inclination is. So if we imagine the path of, let's say, a ball that's been shot out of a ball machine from a point on the ground, and its path looks something like this, if we can zoom into that part, because we know that this angle is changing all the time. So let's imagine now just zooming right into this part here and having a look at it just at the moment that it leaves the ball machine. Then we can look at just that initial moment and actually model it as a straight line just at that initial moment. And we've got the speed there that it's moving. And we can break that speed up into horizontal and vertical components like this just by making a simple right angle triangle. So you can see there that initial velocity might be given to you in a couple of different ways. They might give you x dot and y dot, which is the horizontal and the vertical components of the velocity. They might just say x dot is this, y dot is that. Or they might give it as a vector so that you know what these two lengths will be, whether it's in component form or column form. Now, I think you can see that if you were given these two, then you can actually use Pythagoras to find this. And you can use basic right-angled trig to say, well, what's the angle here? If we know both of these sides, then the angle here would be the inverse tan of this side over this side. So it also makes sense then that they might give you those two things. They might give you the initial speed and the angle of inclination, these two. Because if you had those, then you could find the others from it. You could basically say, I've got the angle, so I can say that the cos of theta would be the adjacent side over the speed, and the sine of theta would be the opposite side, y dot over the speed, and generating those simple expressions there with your basic year 9, year 10 right-angled trig is really straightforward. So you can see that there's 4 pieces of information, the angle and these 3 sides. You'll be given 2, but you can always find the other 2 quite easily. Now, if you rearrange these expressions, you can come up with a little expression here for the initial horizontal component of the velocity and the initial vertical component of the velocity as v cos theta and v sine theta. Now, don't memorize that, because what if you get it wrong and mix them up? I think it's better just to draw your little right angle triangle, no matter which 2 pieces of information you've been given, and then you can find the other 2 really simply and easily from that. That way you don't have anything new really to memorize now, you're just applying skills that you already have. It's also important to note that this little formula here for the initial vertical component of the velocity is not the entire story. We haven't considered acceleration yet. It's actually just the constant of integration, as you'll see in a moment.